If you're a high school student in the United States and love doing math for fun, a competition that you might be familiar with is the AIME. The AIME is the second in a series of steps for U.S. high school students to qualify for the International Math Olympiad. The format for the AIME is a no electronic device, 3-hour test with 15 problems that generally increase in difficulty, and the answer to each one is always an integer from 000 to 999. Every year, 2 AIMEs are given to account for time conflicts. When I was training on past AIMEs in high school, one problem specifically caught my eye. 2019 AIME 1, problem 14. Its position as 14 out of 15 clearly meant that it was difficult, but the statement was one very simple sentence. Find the least odd prime factor of 2019 to the power of 8 plus 1. Not only was it simple to understand, it was a number theory problem, and I love number theory problems. Number theory is the branch of mathematics dealing with, well, numbers. More specifically, number theory considers the properties of the integers, especially the positive integers. Like this one, many number theory problems consider prime numbers and factorization, because finding factors for numbers quickly usually isn't easy. In order to solve this problem, we need to know some important number theory techniques, tricks, and theorems, and my goal is to help guide you through what you need to know and the thought process to solve this problem. An important step in solving most number theory problems is mastering modular arithmetic. But what does that even mean? Let's break it down. There are 3 sets of terms I want to introduce to help when talking about the modular part of modular arithmetic. Modular refers to talking about remainders when dividing by an integer, known as the modulus. This is what the module in modular refers to. For example, 22 divided by 7 would be 3 remainder 1. In this case, 7 is the modulus and 1 is the remainder. We don't need to worry about the 3 since we're only focused on the remainder. Since we are dividing by 7, we would describe this as modulo 7, or as a shortcut, mod 7. In general, to make the notation as easy as possible, if we don't know what the modulus is, I will write it as mod m. If 2 numbers have the same remainder when divided by a modulus, we say they are congruent. Numbers that are congruent to 22 when using a modulus of 7 are 1, 8, 15, 29, 36, and so on. Or even negative numbers like -6, -13, -20, and so on. This is known as a congruence class. Formally, we would write something like this and say 22 is congruent to 36 mod 7. This 3-line equal sign means is congruent to, and is meant to signify that 2 numbers aren't actually equal, but they behave equally when you look at their remainders when dividing by 7. Congruence is equivalent to saying if you have 2 numbers, x and y, such that x is congruent to y mod m, or x is in the same congruence class as y, then x minus y equals km for some integer k. Bringing back the numbers from the previous example, x equals 22 and y equals 36, so x minus y equals -14. Or -2 times 7. Since -2 is an integer, 22 and 36 are congruent modulo 7. When working with numbers in modular arithmetic, it is usually easiest to just look at their remainder. This is because numbers in a congruence class behave similarly, and smaller numbers are easier to work with. This is known as their residue. If you're working modulo m, residues go from 0 to m minus 1. M is not a residue because m has a remainder of 0 when divided by m, putting it in the congruence class of 0. For those of you who like programming, you may be familiar with the percent sign operator. Given 2 numbers x and y, x% gives the residue of x mod y. When a number is replaced by its residue, it is described as reduced. So reducing 22 mod 7 would make it 1. That's everything for the modular part of modular arithmetic, so let's do a quick recap. The modulus is the integer we are dividing by, which I will call m, and we describe that as mod or modulo that number. Congruent refers to 2 numbers with the same remainder mod m, and the set of all integers with the same remainder is called a congruence class. The smallest non-negative number in a congruence class is called the residue, and a number is called reduced if the residue takes its place. Hopefully you've got this down, so let's move on to the arithmetic part. Arithmetic refers to the most basic math operations like addition and subtraction, multiplication and division, and exponents. Starting with addition and subtraction, it's helpful to think that modular arithmetic is like a clock. Instead of the clock having 12 numbers on it, it will have the residues. Keeping with using 7 for the modulus, the clock will have 0 to 6. Addition and subtraction are like moving the hand on the clock forward or backward respectively. A full rotation is the same as adding or subtracting one modulus, so it doesn't matter which number in a congruence class we use to add, because each one will land on the same number in the end. Therefore, we can reduce each term in the expression to get an easier problem. So instead of looking at 22 plus 74 minus 10 mod 7, we can reduce it to 1 plus 4 minus 3 mod 7. In general, if you have two numbers x and y, whose residues are r sub x and r sub y, then x plus y can be reduced to r sub x plus r sub y. If you have more terms like in the example, then just reduce all terms. Multiplication follows easily from addition because multiplication is just repeated addition. Let's try to find the residue of 22 times 74 mod 7. Working it out, we get 22 times 74 is 1628, which when divided by 7 is 232 remainder 4, so the residue is 4. Instead of having to work it out and getting this massive number, we can reduce the factors to get the same effect. 22 and 74 reduce to 1 and 4 respectively, and 1 times 4 is 4, which matches with our first answer. Multiplication in modular arithmetic can be seen as a multiplication of residues. The answer for the multiplication may still fall out of range to be a residue, but the number you get will be far more manageable to find the residue for. Like addition, if there are more terms, each term can be reduced before multiplying them together. When multiplying in modular arithmetic, sometimes two numbers that started with different residues have the same residue after being multiplied. Let's look at numbers mod 10, which is the same as looking at the units digit. If you have 12 and 27, multiplying by 4 gives 48 and 108, which both have a residue of 8 mod 10. If I told you I chose an x such that 4x is congruent to 8 mod 10, and asked you to find the residue of x mod 10, you wouldn't know whether x has a residue of 2 or 7. Let's try to figure out when this happens. Starting with two numbers, x and y, where x is not congruent to y mod m, we multiply by some factor a, so ax is congruent to ay mod m. Using the other definition of congruence, this means ax minus ay equals km for some integer k. Factoring out the a and dividing by m, we get a times x minus y divided by m equals k, where k is an integer. This means that m must divide into a times x minus y. This vertical bar means divides, or m is a factor of a times x minus y. In our example, 10 divides 4 times 27 minus 12, which is 60. There are three possible cases to make sure m divides a times x minus y. Either m fully divides into a, m fully divides into x minus y, or m can be split into factors m1 and m2, both greater than 1, so m1 divides a and m2 divides x minus y. Starting with the first case, if m divides a, then a would be a multiple of m, so ax and ay would be multiples of m as well, meaning ax and ay would both be congruent to 0 mod m. If m divides x minus y divided by m is equal to k for some integer k. If we multiply by m, then we get x minus y equals mk for some integer k. This looks exactly like the definition of congruence mod m, so this means that x is congruent to y mod m. However, we stated earlier that x is not congruent to y, so this case is a contradiction and cannot happen. For the third case, I'm going to leave this one as an exercise for you, the viewer. Since we will only be working with a prime modulus to solve the problem, m cannot be broken into two factors that are greater than 1, so knowing this will not be necessary for the solution. But it is still interesting, especially when it gets combined with division. From the first case, if x is not congruent to y mod p, where p is prime, then ax is congruent to ay only when a is a multiple of p. A corollary of this is if a is not a multiple of p, then ax and ay would also not be congruent mod m. Let's look at a multiplication table of residues mod 7. If I label the rows as r and the columns as c, each entry is r times c. We just learned that if a is not a multiple of p, and x is not congruent to y mod p, then ax is not congruent to ay mod p. On the table, that means no matter which r we choose, as long as it's not 0, multiplying by two different c values and finding their residues, we get two different residues. This means for every row except 0, no residues can repeat, and by symmetry, for every column except 0, no residues can repeat either. Because there are the same number of rows as there are residues, all residues appear exactly once in each row and column, except for the ones for 0. This means if you have an integer x, as long as it's not a multiple of p, then for any residue r, you can find some k so that kx is congruent to r mod p. So when you are dividing modulo p, remember that p is prime, it is always possible to find a unique residue such that reversing the division, or multiplying, will be consistent. Like in normal arithmetic, dividing by 0 is still a problem. This is probably easier to understand with an example. If we divide 22 by 11, we get 2, but reducing everything mod 7, we get 1 divided by 4 is congruent to 2 mod 7. If we multiply both sides by 4, we get 1 is congruent to 2 times 4, or 8, which is consistent mod 7. When performing a divided by b mod p, what we are really asking is, what value of c can we choose so that a is congruent to b times c mod p? If we were given 1 divided by 4, mod 7, we need to look through all residues times 4 to see when we get a match. Luckily, we just learned that multiplying residues still keeps residues unique, so there will be a match, but this is very inefficient, and there are better ways. They just can't fit into this video. There are a lot more interesting things to talk about when it comes to number theory, especially regarding division, but for now, I'll move on to exponentiation. For our problem, we only need to consider positive integer exponents. If we wanted to reduce 22 to the power of 51 mod 7, we can write out 51 22s and multiply them together. Since we know from earlier that we can reduce the factors first, we can reduce this to 51 ones. So 22 to the power of 51 is congruent to 1 to the power of 51, or just 1 mod 7. In general, if you have some base b with residue r, which is raised to some power a, then b to the power of a is congruent to r to the power of a. Theoretically, we are well equipped enough to go at this problem by guessing and checking to see if a prime number divides into 2019 to the power of 8 plus 1. We just need to use our modular arithmetic properties and check to see if the residue is 0. But calculating the residues of powers doesn't always come out as nice as it did in our example. Luckily, there is a trick to reduce the amount of primes we need to look through, and the method behind it deserves its own section in the video. Fermat's little theorem states that for a prime modulus p, a to the power of p is congruent to a mod p. If a is a multiple of p, then both sides can be reduced to 0 mod p. If a is not a multiple of p, using what we learned, we can divide by a. This changes the theorem to a to the power of p minus 1 is congruent to 1 mod p. Fermat's little theorem is commonly seen in both forms, but you have to make sure to specify with the second one that a is not a multiple of p. Let's look back at the example of reducing 22 to the power of 51 mod 7, but let's replace the 22 with a 23. 23 reduces to 2, and the powers of 2 don't behave as nicely. If we use Fermat's little theorem, we can say that 2 to the power of 7 minus 1, which is 2 to the power of 6, is congruent to 1 mod 7. We can split 2 to the power of 51 as 2 to the power of 6 to the power of 8 times 2 to the power of 3. Since we know that 2 to the power of 6 is 1 mod 7, and 2 to the power of 3 is 8, this is congruent to 1 to the power of 8 times 8, which reduces to 1 mod 7. Let's prove Fermat's little theorem. There is a very elegant proof using necklaces, which has been covered on other channels, but I would like to use a different proof. The proof will also introduce a concept that gives us a key insight that the necklace proof doesn't give us. This concept is known as multiplicative order. The order of a number n mod m, sometimes written as ord sub m of n, is the smallest positive integer x, such that n to the power of x is congruent to 1 mod m. For example, the order of 2 mod 7 is 3. If we list out the powers of 2, the first positive integer x, such that 2 to the power of x is congruent to 1 mod 7, is when x equals 3. After this point, the residues will cycle. because multiplying 1 to 2 will get us back to 2. If we continue following the cycle, raising n to any multiple of the order will also produce a residue of 1 mod m. If you noticed, 51 is 3 times 17. Since 51 is a multiple of 3, and 3 is the order of 2 mod 7, 2 to the power of 51 has a residue of 1 mod 7. Conversely, if you have some integer y such that n to the power of y is congruent to 1 mod p, then y has to be a multiple of the order x. Before we continue, we should also prove that the order exists for any n modulo some prime p as long as n is not a multiple of p. If we keep track of all the residues of n to the x mod p, we will notice two things. The first is that the residue is never 0. Otherwise, p would divide n to the x. This means p would also divide n. This contradicts the statement that n is not a multiple of p. The second is that the residues must repeat at some point. There are only p-1 non-zero residues, and if we pick a range of p powers, like n to the x, where x is between 1 and p, there must be at least one repeating pair of residues. We can pick a repeating pair and label the smaller one n to the a, and the larger one n to the a plus b. So n to the power of a plus b is congruent to n to the power of a mod p. Since division is allowed because n to the power of a is not congruent to 0, and the modulus is prime, we can divide by n to the power of a to see that n to the power of b is congruent to 1. Let's look at how all the residues behave when multiplying by 2. 0 goes to 0, 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 1, and so on. If we put all the residues in a circle and draw arrows representing which numbers go where after being multiplied, they form cycles. Starting at 2 and following the arrows is like exponentiating because following an arrow multiplies by 2. Because the order exists, we know that the cycle containing 2 also has 1 in it. And because any number multiplied by 1 is the same number, 1 points to 2. The entries in this cycle do not repeat until we return to 2, so the length of this cycle must be the order of 2 mod 7. We can get the other cycle by multiplying the numbers in this cycle by 3 and reducing. In general, if you pick a number n and find its order mod p, remember p is prime, you can generate all cycles by first finding the cycle that n is in, which will also have 1, and the length of this cycle is the order of n mod p. To get the other cycles, we pick a residue that is not in the original cycle, multiply by that residue, and reduce. This will guarantee that that cycle will have that residue because we had 1 in the original cycle, and we know that the cycles won't mix because multiplication is unique mod p. These cycles split the residues into sets. Each set is a cycle that contains all the integers in their set exactly once, and they all have to be the same length as the original cycle. The only exception is 0, which is always in a cycle of length 1 because multiplying by 0 always makes 0. So with our p residues, after taking out 0, we are left with p-1 residues, and we have to split these p-1 residues into equal length cycles. This means that the lengths of our cycles must be a factor of p-1. The final piece is that our original cycle has a length equal to the order of the original number n, so the order of n mod p must divide p-1. Now that we have this, let's finally prove this version of Fermat's little theorem. For a prime modulus p, a to the power of p-1 is congruent to 1 mod p, when a is not a multiple of p. Using what we just learned, the order of a mod p divides p-1. Let's call the order x. Because x divides p-1, we know that p-1 equals x times y for some integer y. Since x is the order of a mod p, we know that a to the x is congruent to 1 mod p. We can raise both sides to the power of y to get a to the power of x to the power of y is congruent to 1 to the power of y, or just 1 mod p. Using exponent laws, the left side is equal to a to the power of x times y, and we just defined that x times y equals p-1, so this is equal to a to the power of p-1. Thus, a to the power of p-1 is congruent to 1 mod p. With that, we have completed our proof of Fermat's little theorem. Now that we have all the tools needed to solve the problem, let's actually solve it. The problem states, find the least odd prime factor of 2019 to the power of 8 plus 1. If you want to solve it by yourself, pause the video now because now is your last chance to try it. Let's start by calling the prime we want p. Since p divides 2019 to the power of 8 plus 1, 2019 to the power of 8 plus 1 is congruent to 0 mod p. We can subtract both sides by 1 to get 2019 to the power of 8 is congruent to negative 1 mod p. This is very close to the form we want, so we can apply Fermat's little theorem, but we want a positive one, not a negative one. A couple of things we don't want to do is to add 2, because then we would have a plus 2 on the left side. And we don't want to multiply by negative 1, because then we would still have the negative, but on the left side. Instead, the trick is to square both sides. By squaring both sides, we get 2019 to the power of 16 is congruent to 1 mod p. This is perfect. Now we have the exact form we want. If we add 1 to 16, we get 17, which is a prime number. So we can use Fermat's little theorem to prove that 2019 to the power of 16 is congruent to 1 mod 17. This means 17 must be our answer. We can test this by hand, which is what you need to do on the test, but to be quick, I will test it by putting it into a computer. If we ask a program to print the quantity 2019 to the power of 8 plus 1 % 17, we should get 0, because Fermat's little... Wait, what? Okay, so what we need to be careful of is the fact that 2019 to the power of 8 is congruent to negative 1, but 2019 to the power of 16 is congruent to positive 1. We established that if you have some power y, such that n to the y is congruent to 1, then the order must be a factor of y. In our case, y equals 16. Since 8 is not the order, and any smaller factors would contradict 2019 to the power of 8 being congruent to negative 1, the order must be exactly 16. 2019 has an order of 4 mod 17, so 17 isn't actually the prime number we want. Another thing we learned from earlier is that the order 16 has to divide p minus 1. This means p minus 1 is congruent to 0, or p is congruent to 1 mod 16. Unfortunately, this part is a bit of guess and check. Because this is an AIME problem, we know that our answer has to be between 000 and 999. And if we were preparing for an AIME, we would know there are 168 primes in that range. If we want to know the number of primes that are congruent to 1 mod 16, we can approximate it by assuming that the primes are roughly equally distributed among the odd residues. This tells us that there are about 21 primes below 1000 that are congruent to 1 mod 16. In fact, there are 19 primes, so the approximation is pretty close. Checking 167 primes in 3 hours is incredibly difficult and probably impossible, but checking about 21 primes is definitely possible. If we were to put ourselves in the mind of the question writer, they probably do not expect us to know the higher valued prime numbers, so we should expect the answer to be relatively small. Let's look through the next few numbers where an integer m is congruent to 1 mod 16. We know 17 doesn't work, and we want m to be prime, so 33, 49, 65, and 81, which are all composite, won't work either. This means 97 is the next prime we have to check. We can check this by hand or with a computer, and luckily for us, 97 is the prime that we want. We finally got what we wanted. The least odd prime factor of 2019 to the power of 8 plus 1 is 97. At the end of the solution by the MAA, the organization that runs the AIME, they write 2019 to the power of 8 plus 1 equals 2 times 97 times p, where p is the 25-digit prime 1423275002072658812388593. At least they have it for completeness. Despite being a very simple statement on the surface, it did require learning or knowing quite a lot of number theory knowledge in order to solve it, and there were also a couple of interesting snags. Specifically, 2 parts of the solution are really important to acknowledge. The first is the step where we square 2019 to the power of 8 congruent to negative 1, turning the negative 1 into a positive 1. It's quite subtle, and if you're not familiar with it, squaring might not come to mind immediately. The second is noticing that 17 is not the answer to the question. When squaring, or working in modular arithmetic, it's very easy to miss when a solution isn't actually a solution, and this is why it's important to check your answers. After that, applying everything else we learned in this video should give us a smooth ride to finish the problem. Not only do we need to know the basics, we also need a couple clever ideas to solve the problem correctly. This combines to create a great instructive problem despite its simple appearance. Thanks for watching, and I hope to see you in another video.